Hello, good morning student. How are you? I hope you all are happy and healthy at home. So what did we discuss yesterday? We discussed yesterday about the protection and deprotection of aldehyde and ketone as an acetal formation and the ketal formation. Similarly, that is a thioacetal and thioketal formation. In what condition these groups are introduced, in what condition they are removed, as well as in what condition they are stable. So that type of the thing we have learned, we have discussed yesterday. Today, what we are going to discuss today, let us see here, that is a peptide synthesis, because it is a real application now we are going to learn for the protection and the deprotection in a peptide synthesis. The two amino acids are joined together by a peptide bond or amide linkage is known as peptide synthesis, and that is a peptide are naturally occurring polymers of amino acids, and as we know that amino acid, there are naturally occurring 20 amino acids are there, and all our amino acid are in a L configuration, and as we know that L and capital L and capital D are the relative configuration, and whereas S and R are the absolute configuration. Don't mix these two terms together, but remember there are 20 amino acids are there, and there by using those we are going to synthesize the peptide synthesis. Just now I had told you that these are having as a L configuration, and what is the, and as we know for the peptide synthesis the smallest unit is known as alpha amino acid. If you look at these alpha amino acid, some of the amino acids are acidic in nature, some of them are basic in nature, and most of them are neutral in nature, and nearly the 20 amino acids, and I am given the list of those 20 amino acids over here. But here, what is the general formula of amino acid? What are the functional group present in the amino acid? Let us see here. The general formula of alpha amino acid is R, then CH, then NH2, then C double bond O, OH. This is known as alpha amino acid. Why it is called as alpha amino acid? If you observe this structure carefully, what do you see over here? This is a carbonyl group. Adjacent carbon atom is termed as alpha. At alpha position there is a amino group, and as we know that amino group means the nitrogen atom containing as a lone pair, and it is readily available for donation, and therefore it is there. And this is the acid. Why it is acid? Because here this proton is highly acidic in nature. It get dissociated. Extent of dissociation means number of H plus produces, the acid strength of acidity goes on increasing, and therefore the name of this is a general formula of alpha amino acid. This is a general formula of alpha amino acid at alpha position, and the nature of R is different one. We will get as a 20 alpha amino acids over here. This is now and these alpha amino acids are present in Jupiter ion. Do you know the Jupiter ion? Jupiter ion means here this lone pair can pick up the proton over here, and you are going to get the structure R, then CH, NH2, positive charge over there, and this C double bond O minus. Look at here, positive and negative charge present in the same structure. That type of the ion is called as the Jupiter ion. This type of the Jupiter ion, this type of the species is known as a Jupiter ion, because here amino, here let us see here NH3, not the 2. Here NH3 positive charge on the nitrogen atom, negative charge on the oxygen atom, and that type of the ion is called as a amino acid. It is one of the feature of that amino acid. Now just now I told you that all naturally occurring amino acids are L configuration, and as we know that in a carbohydrates the reference compound we are taking as a glyceraldehyde. Everybody knows the structure of glyceraldehyde is, and these normally carbohydrate as well as these alpha amino acid, they are written according to as a Fischer projection formula, and you might be knowing there are 4 ways to represent the organic molecule on a blackboard, because a blackboard, or what we can call it as a book, has a 2-dimensional. You have to study, you have to imagine the molecule in 3-dimensional, and therefore these are the 4 traditional method for representation of the organic molecule on the blackboard, so that we can visualize the 3-dimensional structure of the organic molecule. Number 1 is a Wedge formula, number 2 is a Sawhurst or Andrew formula, number 3 is a Newman projection formula, and number 4th one is a Fischer projection formula. According to as a Fischer projection formula, we are writing the structure vertically, and suppose here is a OH on a left hand side, and here generally CH2OH, and as we know that carbohydrates are polyhydroxyaldehyde or ketone is known as a carbohydrate, and the simplest one is this one. This is called as a triose, or it is known as a glyceraldehyde. It is a precursor for the carbohydrate, and now it is designated as a D-glyceraldehyde. D-glyceraldehyde. Why D? Look at here, OH present on the left hand side, and that's why it is designated by the D. Suppose if you put as a mirror over here, what do you see? Its mirror image, hydrogen atom OH, CHO, and then this one is a CH2OH. Here you can write H2C, then HO. Exact mirror image, and this one is called as a L-glyceraldehyde, and D, capital D and capital L are the relative configuration, and R and S are the absolute configuration, and they don't have a relation, and these compound are chiral. These amino acid, most of the amino acids are the chiral in nature. Chiral means what? Or these organic compound at the chiral in nature means the atom containing the 4 different group. The carbon atom carrying the 4 different group are known as chiral center, or we can call it as a asymmetric carbon atom. Asymmetric carbon atom is nothing but as a carbon atom carries 4 different group is called as a chiral, and the organic compound has a chiral center. That compound is optically active in nature. Optically active in nature, and as we know that optical activity, it is one of the physical property of the organic compound. If the organic compound are chiral in nature, that compound must be optically active in nature. The instrument used to determine the optical activity, the name of that instrument is a polarimeter. Do you know that polarimeter is an instrument used to measure the optical activity of the organic molecule? And all chiral compound shows the optical activity. What do you mean by or what does it mean optical activity? Any substance which rotate the plane of polarization through the certain angle is known as optical activity. And a few milligram of the sample dissolve in a proper solvent and put in a polarimeter, there will be a deflection occur, means optical rotation is obtained either right hand side or left hand side, leo-rotatory or leo-rotatory or dextro-rotatory, and that's on that basis we can easily find out the given compound is optically active or optically inactive in nature. Now here, according to as a Fischer projection formula, what you have to show, you have to keep the most oxidizable group here normally as a carboxylic COOH over here, right? And now on the left hand side you can put as a NH2 group, and then there will be here hydrogen atom, and here you can call it as a R over here. Now now remember, all naturally occurring amino acids are L configuration, means they are having as a S configuration. R and S configuration are the absolute configuration, and for that R and S configuration, look at here, this S2N present on the left hand side, and therefore it is known as a L alpha amino acid. Alpha amino acid. If you put as a mirror over here, what do you see here? You can see NH2 over here. This is a COOH, and they are mirror images of each other, and they are known as a enantiomer. Enantiomer you might be knowing. Enantiomer means what? They are non-superimposable mirror images of each other, are known as a enantiomer. Here, if you see this structure, if you observe this structure carefully, alpha amino acid, and these alpha amino acids are normally S in configuration. Yes in configuration, but S configuration, how to assign that? Here is a chiral carbon atoms are there. Now look at here, carbon atom, here is a nitrogen atom. A nitrogen atom is a bigger, there is a CIP rule. CIP, or we can call it as a sequence rule. CIP means they are the scientist name. C stand for Khan, I for Ingold, and P for Prelog. These are the three scientists studied that and formulated some rule, and that's why it is called as a CIP rule or sequence rule. The arrangement of group according to their priority around the chiral carbon is known as a sequence rule, and therefore there are the four rules are there. Number one is called as a atomic number. Second one is a next atom. Third one is a double bond or triple bond, and fourth one is a isotopes. Fourth one is isotope, and as we know that isotope means what? Isotope atomic number are same, but their mass number are different. For example, hydrogen has three isotopes: hydrogen, deuterium, and tritium. Hydrogen 1, deuterium 1, and tritium 1, all are having as the same atomic number, but their mass numbers are different. Hydrogen 1, deuterium 2, and tritium 3. So that are the mass numbers are there. And now why it is a S configuration? Look at here. nitrogen atom and this is carbon atom, it will get the first priority, it will get the second priority. Now if R is equal to hydrogen atom, that molecule becomes as a achiral. Remember, chiral means what? Chiral, and second one is achiral. Both are totally different. Chiral means the carbon atom attached to 4 different groups are known as a chiral. Achiral means 2 or more than 2 groups are identical attached to that carbon is known as a achiral carbon, or that is optically. This one shows as a optically inactive nature. Optically inactive. Optically inactive, and chiral carbon, they are optically active in nature. Optically active in nature. This is the term you should remember over here. Now, how they are showing as R configuration? Look at 1, 2, and here maybe as a 3. 1, 2, 3. That is actually as a R. But look at fourth priority group. If it is present at horizontal, then its configuration is reverse, inverted, means that R changes to S, means this has S configuration, that are the alpha amino acids. Now, and for the synthesis, how that peptide bonds are occur, before that, let us see the structure of these alpha amino acids. Number one, suppose we have a general structure R, then CH, COOH, and here is a NH2, right? These are, suppose I am taken as a hydrogen atom. So first one, the structure of glycerine, structure of glycine, right? And what is the structure here? Just take as a hydrogen over here, CH, then NH2, and then COOH. This is the structure of glycine, and glycine are soluble in water, and most of the amino acids are soluble in water because they are having as a polar in nature, and that's why, and as we know that one proverb is there, like dissolve in like, polar dissolve in polar, non-polar dissolve in non-polar, and therefore most of the amino acids are soluble. Then glycine is soluble in water. And now tell me whether this glycine is optically active or optically inactive nature. Is there a chiral carbon present in this glycine? Look at here, this is a carbon atom, only one two, but it is a functional group there. Look at this carbon atom, there is a 2 hydrogen atom, 1 and 2. 2 groups are identical, and therefore glycine is achiral in nature. Achiral in nature, and therefore it is optically inactive in nature. This glycerin is optically inactive in nature. Here is R is equal to hydrogen is taken here, and that is the structure of glycine. Now is the alanine. Second one is a alanine. What will be the structure of alanine? If you take R is equal to here CS3 group, you will get the structure CS3, then CH, COOH, and this one is a NH2, where you can take R is equal to here methyl group. So that is the structure of alanine, right? So what if R is equal to H, that is called as a glycine. If R is equal to methyl group, that is called as a alanine. And alanine, third one is a valine, right? Third one is a valine. Third one is a valine. Here if you take R is equal to, isopropyl group here R is equal to isopropyl group like this, CS3, then CH, CS3, rest of the thing remains as it is, CH, COOH, and here is a NH2, this, where R is equal to which group we have taken? This one, CH, one methyl group here and one methyl group over here. This structure is known as a valine. We have seen the structure of glycine, structure of alanine, structure of valine, and structure of leucine over here. The structure of leucine will be, the structure of leucine is here. The structure of leucine will be, instead of leucine structure, fourth one is the structure of leucine. What is that leucine? Leucine, leucine. Here just you insert the CH2 group over here, CS3, then CH, CS3. We inserted CH2 group and rest of the thing remains as it is. NH2, COOH is known as leucine, where here R is equal to taken as CH2, then CH, this methyl group and this methyl group. We have seen the structure of leucine. Now let us look at as a structure of isoleucine. Structure of isoleucine. So here just fifth one, structure of isoleucine. The structure of isoleucine will be like this. Here CS3, CH2, then CH. Here one side CS3 and there CH, NH2 and C double bond OH is known as a isoleucine. What is there? Only skeleton of that, the nature of group, R group is changed. Here R, then CH, CH, on this side CH2, CH3 ethyl group, and other side will be this one, R is equal to CS3, and that is a isoleucine. Leucine. So that is the structure of isoleucine. Now let us see the another structures of on 6 onward. What are the structures of those? Let us see here. The structure of phenylalanine, right? 6 number structure of phenylalanine. Phenylalanine structure is here like this, or you can in short write pH, then CH2, then CH, C double bond OH and NH2. This part remains as it is, only R group is changing, and that is why it is a structure of phenylalanine, where R is equal to here CH2 and the pH. This is the structure of phenylalanine. Now is a structure of what is that? Tyrosine. 7th one, the structure of tyrosine. The structure of tyrosine will be like this. Only this part remains as it is, means CH, C double bond OH and NH2. This group remains as it is. There will be this one phenol attached to this, and the R is equal to this one phenol type of the group, and that is known as a tyrosine. We have seen the structure of tyrosine. Now let us look at as a structure number 8 is a serine. All are the amino acid structure. The common alpha amino acid remains as it is, CH, C double bond OH and this NH2. What is the R group over here for serine, or for serine is this one. Here just CH2 and OH group, and where here is R is equal to CH2OH group is attached, and that's why it is called as a serine. Now is a structure number 9, which is structure number 9 is a cysteine, right? That is a cysteine. The structure of cysteine will be this one. Instead of here HO, there will be a sulfur atom. Here HS, CH2, then CH, NH2, C double bond O, OH, where R is equal to this one CH2SH. Instead of oxygen atom, there will be a sulfur, and that is the structure of cysteine. These are some of the structures of amino acid we have seen up to the 9. Then let us see the next structure of the alpha amino acids are this one. Now is a 309. 10th one is a 309. The structure of 309 will be only just this remains as it is CH, C double bond O, OH, and this NH2. Here CH, one side there is a CS3 and OH, where R is equal to this CH, then CS3OH. This is known as a 309. Now is a 11. 309 we have seen, that is a methionine. The structure of methionine will be this one. This part remains as it is CH, C double bond OOH, then NH2. Here attach as CH2, then CH2, then Me3. This is a CS3, and where that's why it is R. The nature of R is equal to here CH2, then CH2, CS3, and that is known as a methionine. Now let us look at as the next structure is a tryptophan. 12th one. The nature of that tryptophan is a structure of 12 tryptophan. Instead of this one, this part remains as it is CH, tryptophan. The structure of tryptophan will be this one, CH, C double bond O, OH, then NH2, and what is here attached this CH2, and then there will be this group benzene ring attached to this one indole. That is a indole type of the structure, and therefore this is known as a structure of tryptophan. This indole moiety attached via or through CH2 group, that is known as a tryptophan. The next one is a 13 number is a lysine. Structure of lysine. 13 number is a structure of lysine. The structure of lysine is a this one, CH, C double bond O, OH, then NH2, then CH2, 4 times, then H2N. This is a basic in nature. Why it is a basic in nature? Look at here. There are the 2 amino groups are there, and therefore this lysine is nothing but as a base over there. Now this one same is there, therefore it is a neutral. If you see over here, this will be the neutral, this is also as a neutral. Most of the amino acids are neutral. Here we find lysine is a basic in nature. Now let us see, next one is a RJ9. Next one is a RJ9. What will be the structure of RJ9? Let us see here the structure of RJ9. What is that? 14 number structure of RJ9. The structure of RJ9 will be 14 number. This is also as a basic in nature. Here, as we know that CH, then C double bond O, OH, and this NH2, and this further attached to CH2 4 time, CH2 not 4th time, 3 time, and then NH further attach with this CH double bond NH and the H2N. So this is a structure. Again it is RJ9 also as a basic in nature. Look at, there are number of nitrogen NH2 groups are greater, and therefore it act as a basis. Now next one is a aspartic acid. Name itself suggests that is a acidic in nature. 15 number aspartic acid. Aspartic acid. The 15 number itself suggests that the structure there may be a 2 acids. Here CH, then COOH, then NH2 group is there, and then here attach as another OH group, and that is a structure. No, one more CH2 group here, CH2, and then attach carbonyl group, carboxylic group. Look at here, this is why it is acidic in nature, because there are 2 carboxylic groups are present, and therefore aspartic acid is acidic in nature. Now let us look at as a next one, 16 one, that is a glutamic acid. This one is a glutamic acid. The structure of glutamic acid will be, name itself suggests that is acidic in nature. Let us see here CH. Here R group is this one, right? R group is this one, and here CH, COOH, then NH2, and then this group further attached to 2CH2 group, CH2 twice time, and then COOH. That is also as acid. Here R is equal to CH2, C double bond OH. Here R is equal to CH2, then C double bond OH, right? So that is the structure of glutamic acid. Now next one, asparagine, right? 17 one is asparagine. Asparagine. What will be the structure of asparagine? Let us see here the structure of asparagine. Again basic is this one is a neutral in nature, again CH, NH2, then C double bond OH, and here further attached with this CH2 twice attached to as a amino acid, this one H2N, this one, and that's why it is known as a asparagine. Now is let us see the next one. The next structure will be, what is that? That is a glutamine. 18 one is a glutamine. What will be the structure of glutamine? The structure of glutamine will be this one, CH, C double bond OH, then NH2, here CH2 twice, then C double bond H2N, that is also as a neutral in nature, glutamine. Now is a 19th number, that is a histidine. Histidine, it is one of the antifungal drugs. So amino acids, that is histidine. The structure of histidine is this one again, CH, then C double bond O, OH, NH2, and this further attached to CH2, and there will be a 5-membered ring at N, then N attached over here, H double bond, alternative double bonds are here, here a double bond and here. So that is a structure of histidine. And finally the structure of proline. And remember, the structure of proline is a secondary amide here, H and C double bond OH. This is the structure of proline, which is different than the rest of the thing. So in this way we have seen all the structure of amino acid. In the next lecture we are going to synthesize this peptide by protecting one of the group, maybe as amino, and we are going to activate that carboxylic group treated with another amino acid. There is a peptide synthesis. In this way we are going to synthesize different type of the peptides are there. How that we will see in the next lecture. Let us stop today here. Have a nice day. Thank you.